Thank you so much for having me. Thank you so much for inviting me. Can you guys all hear? Is the volume okay? All right. I'm so pleased to be here to talk to you about our work, to share with you the results that we've had from Kepler. This is a Bay Area mission. This is one of the most exciting things NASA's got going on right now. It's yielding very good results, very amazing and exciting results, and I'm really happy to be here to share that with you. Kepler is a mission to find planets orbiting other stars. We call these exoplanets because they're outside of our solar system. It's setting out to do something very, very specific, to answer a very specific question. And that question is, are potentially habitable Earth-sized planets abundant in our galaxy? That's what we're setting out to do. So before I get too much into the details about how we're doing this, and then to share with you some of the results that we've had over the last couple of years, I want us to stop for just a second and think, what are the ingredients for life? I'm sure you guys could come up with a laundry list of items, right? Okay, well, we need oxygen, right? And we need nutrients and some kind of energy, right? And red wine, of course, is right up there. And but there might be some that are less obvious. What about a moon to protect us from collisions? What about a magnetic field to shield us from harmful particles, right? So what we do is we look at examples of life on Earth. And we say, well, is there something that all of these organisms have in common? Is there one unifying thread that all of these organisms rely on? And the problem is that life here on Earth is extremely diverse. The very first life forms here on Earth were, we think, the cyanobacteria. And these microbes, this blue-green algae, is the oldest fossil that we've ever found, 3.5 billion years old. The Earth is not much older than that. And that's what's depicted on in the upper left-hand corner are the fossils of these cyanobacteria that were from the Archean age found in Australia. And they don't require oxygen. Okay, so all right, let's scratch that off the list. On the right-hand side, we've got a satellite image of Lake Vostok. It's a lake in Antarctica at the polar cap. What you don't realize from this image is that the radar penetrates about 2 miles worth of ice that's covering the lake. This is a subglacial lake. And some clever scientists went down there and they drilled an ice core down into that ice covering the lake, and they pulled it out and they cut it up and they started looking at what was in that ice. And then the ice core that they drilled out stopped about 100 meters above the surface of the water so that they didn't cross-contaminate the water. And they pull it out, and what do they find? They find dormant microbes right above where the surface of the water was. How did they get there? Right? Presumably they came from the water underneath, which suggests that there might be things living there, things that require very little energy in terms of the energy that we think about, like the sun, right? Likewise, on the other end of the spectrum, we've got things that survive, like these microbes living in the thermal pools in Yellowstone, that survive temperatures in excess of the boiling point of water. DNA seems to break down, loses its cohesiveness at around 150 degrees centigrade. So there are organisms there that survive, reproduce, function at 120 degrees Celsius. So life is very diverse. Under every rock, we find something living. But the one thing that all of these organisms have in common is that they are carbon-based. No matter where on the tree of life, the cyanobacteria over there in the blue circle, animals, plants up there in the green, the archaea down in the bottom, no matter where on the tree of life you are, the organisms are carbon-based. And organic chemistry, as far as we understand it, at least here on Earth, requires liquid water as the solvent which facilitates the reactions like metabolic reactions and all of the things that we know of that produce life and make life thrive. So there are scientists that think about other alternatives to life. Maybe instead of H2O, we're going to go down the periodic table and go in the same line. We're going to find sulfur right underneath oxygen, and maybe you could substitute the oxygen for sulfur and have the same kind of thing happen. And certainly there are people thinking about that. But here on Earth, what we see is life requiring liquid water. So we're going to chase the water. When we talk about a potentially habitable world, we're talking about a world where liquid water could pool on the surface. Liquid water being the underlying common thread. So therein arises this term that we use all the time, and you guys have probably heard it because it's always in the media, habitable zone, right? The habitable zone around a star. And the habitable zone is simply the region or the distance from a star at which you're not too cold, not too hot, so that water could exist in a liquid state on the surface, could pool on the surface. And so there are various ways of calculating that. And we assume the very simplest, which is just to take the equilibrium temperature. You know, you're standing a certain distance away from a campfire. How much heat do you feel in your hands? How much radiation do you feel? And so the habitable zone, that Goldilocks zone where liquid water could pool